Okay, then let's get started. So let's do a quick review of meters. Last time we looked at meters, and we looked at some of the more advanced features that they could do for us. We looked at their ability to measure frequency, capacitance, and high current, right? So first of all, let's talk a little bit about frequency and discuss what that was before we talk about how we measured it. So we said that frequency is how often something repeats, okay? And we said that the most common unit for frequency in electronics is given in cycles per second, right? So if something happens 5 times in a second, we would say that was 5 cycles per second. What was the name for that unit?
Hertz.
Hertz, that's right. And that's abbreviated Hz. I think it's actually a Z on the end. So if it was 5 times a second, we would say that's 5 hertz, right? There are other units of frequency that we could talk about also. If we're talking about automotive applications, you might talk about RPM for the motor, right? That's revolutions per minute. So that's how many times a revolution happens in a given period, a minute. So that would be another unit of frequency. But the unit that we use most often in electronics is hertz, cycles per second, okay? And we said that the frequency is related to another quantity, the period. We said that the period was the amount of time that it takes for one cycle to complete. So if something is happening 5 times in a second, that means that each cycle lasts for 1/5 of a second, right? So we have a formula that allows us to calculate the period if we know the frequency, or calculate the frequency if we know the period, right? We could say frequency equals, what was the formula?
1 over the period.
Yeah, 1 over the period. And similarly, the period equals 1 over the frequency, right? So that's a little bit about what frequency actually is. We said that we could use the meter to measure frequency, right? There's a frequency position, and you just move the dial over into the position where it says Hz for hertz, and then the meter will measure frequency for you. Okay. Any questions about frequency? Okay. Then we talked briefly about capacitance, right? So we talked about capacitance and capacitors. We said that capacitors are fairly simple devices, right? At the most basic level, a capacitor is just 2 plates of metal that are close to each other, right? And they're separated by some layer of insulating material. Anybody remember what this insulating material was called in between them?
Dielectric.
Yeah, the dielectric, exactly. Okay. So we said that the way that capacitors actually work is that we attach a wire to each plate, and then we can put a voltage on these wires. And this voltage causes charges to move onto the plates. So if you have a positive voltage over here, it pushes little positive charges onto this plate, and they start to build up. And those positive charges repel other positive charges, So you have other positive charges pouring off the opposite side, and then the positive charges attract negative charges. So you end up getting a bunch of negative charges attached to the opposite plate. Okay? So even when you remove the voltages from these wires, you still have energy stored in this capacitor because the positive charges over here are still attracting the negative charges on the opposite side. So you still have these two separate charges on the two plates. So that's really the main purpose of a capacitor, is to store up energy and discharge it when you want it to be discharged. Okay? So there were three main factors that influenced how much capacitance we had in a capacitor, right? Anybody remember one of those factors? Yeah.
Distance between the plates.
Yeah, distance, exactly. So we said that just like magnets, the closer electric charges are to each other, the harder they pull on each other. So if you have the plates really close to each other, the positive charges attract a lot of negative charges, and so you can store more energy. So the closer the plates are to each other, the more energy you can store. The farther away they are, the less you store. Yeah?
Oh, I was going to say the dielectric material.
Yeah, the dielectric material is another one, exactly. Different dielectric materials have different properties which result in different amounts of charge being stored on the plates. And then I think you mentioned the last one? Yeah, the plate area, exactly. The larger the plates are, the more charges you can store on them. So the more capacitance you have. Okay? So this is the basic idea behind capacitors. We're going to talk more about them in a later lecture, and we're actually going to get to build our own capacitors. But this is sort of the fundamentals of capacitors. And we said that we could use our meters to measure capacitance. Now, did we use the long leads to hook up to our capacitor before we measured it? No, we didn't. Why not? Yeah, exactly. Yeah, the leads can be, they can create their own capacitance and they can throw off your measurement. So instead of using the leads, we just pushed the two legs of the capacitor into those little slots in the meter and measured the capacitance that way. Right? Okay, so that was a little bit about capacitance and how to measure it. Any questions about that? Okay, and then the last thing that we measured with our meters last time was high current. So there's not a lot of theory behind high current, right? It's just regular current, it's just a little bit more of it. But we said that when we wanted to measure high current, we had to move the red lead into the farthest left-hand hole in our meter, right? The hole that said 10 amps. And when we did that, there was only one place where we could put the dial, right? We had to turn the dial so that the arrow was pointing to the little indicator that said 10A, okay? If you move the dial into the other spot on the current measuring location, it'll still give you a reading. It won't tell you that anything is wrong, but the reading will be 10 times bigger than it should be. Okay? So this is a very easy mistake to make. There's no real indication that you're doing it, except that the dial is in the wrong place. So remember that when you're measuring high current, the lead has to be in the hole that says 10A, and the dial has to be in the position that says 10A. Okay? So, any questions? Yeah?
What was the delineator between high current and low current?
So, in the low current region, you could either measure 20 milliamps or 200 milliamps. So, anything up to 200 milliamps could be measured in the low current setting. And then above that would have to be measured in the high current setting. Yeah. Other questions? Okay. So that was a little bit about meters, like we talked about last time. So today, we're going to talk about diodes and transformers. Now, diodes and transformers are two very different components. So you might ask why we would talk about these two different things on the same day. Well, what happens is that both of these components are used to make power supplies. Okay? Like the little power supplies that you plug into a wall if you're going to charge up your phone, or the power supplies that are on your bench, the kind of power supplies that take AC electricity that comes out of the wall and turn it into DC electricity that can be used to run most electronics, like charging phones, doing experiments on the bench top, running computers, things like that. So diodes and transformers are used as part of the power supplies. And next time we're going to talk about how to actually create power supply circuits. So we're going to talk about what goes on inside of those circuits. Today we're going to talk a little bit about diodes and transformers themselves as components so that you know a little bit about it so that you're ready for next time when we talk about power supply circuits. Okay? So let's start by talking a little bit about diodes. So what are diodes? The fundamental purpose of a diode, or the thing that it really does, is that it acts like a one-way valve for electricity. It allows current to flow through in one direction, but it blocks it and prevents it from flowing back the opposite way. Okay? So that's the fundamental thing about diodes. If you only remember one thing about diodes, that's what you should remember. Okay? So let's talk a little bit about what they actually are, what they look like. So if you were to look at the body of a typical diode, it looks kind of like this. It's sort of cylindrical. And it's mostly black, but it's got a band around one end. Okay? So I brought one of these with me. I'll pass it around. You guys can take a look at it. This is the sort of typical diode that we'll be using most often in our classes. You might see that most often in circuits that you build or analyze out in the world. But diodes also come in other shapes and sizes as well. So this would be an example of a really big diode. This would be a diode that might be found, I believe this came from an aircraft of some kind. So it serves the same purpose. It allows electricity to flow through in one direction and prevents it the other way, but it just can handle more current, so it's larger. Okay? Yeah?
What's the rating on the small one here?
In terms of how much voltage you can handle?
Yeah.
I don't know off the top of my head. I have to look that up. But it's less than the big one. So if you look at the circuit schematic diagram for a diode, it looks like this. So it's got two different sides. This side over here is called the anode. and that's abbreviated A. And the other side is called the cathode. And that's abbreviated K, because an engineer made it up, and engineers can't spell. Okay, so I know this because I'm an engineer. So the diode has these two sides, and if we put a positive voltage on the anode and a negative voltage on the cathode, then we say that the diode is forward biased. And in that condition, electricity can flow through it. Okay? And when the electricity flows through it, there is a small voltage difference between the anode and the cathode. It's usually somewhere between 0.5 and 0.7 volts. Okay? We'll call it 0.6 volts. It's not really precise. It can vary a little bit, but it's somewhere in that range. Okay? So it doesn't change much based on how much current is flowing through the diode. So if you have a little bit of current, it's about 0.6 volts. If you have a lot of current, it's still about 0.6 volts, somewhere in there. Okay? It always stays about the same. That's different than the way that resistors work, right? With resistors, we know that V equals I times R, right? So the more current you have, the more I, the more voltage you have, right? Diodes are different. They're always about the same voltage across them, no matter how much current is flowing through it. Okay? So it's a little bit different. So if we put a positive voltage over here, negative voltage, we say it's forward biased and the electricity flows. If we put the voltage in the opposite direction, so we have a negative voltage over there on the anode and a positive voltage on the cathode, this is reverse biased. And in this case, no electricity flows. So like I mentioned at the beginning of class, the diode is acting like a one-way valve. If you try and push electricity through from the anode to the cathode, then it works just fine. If you try to push electricity through in the opposite direction, then the diode blocks that, and the electricity cannot flow. Okay? So it acts like a one-way valve. Yes?
Is the cathode, is it using that 0.6 voltage? Is that what it's using to hold it back? Is there some, why is the voltage drop?
Yeah, so it's a little bit complicated. So we can talk about that briefly.
If it's way too far off subject, it's fine.
No. It's on subject. It's just a little bit complicated. But let's talk about it briefly. Okay? So it comes down to the type of material that the diode is made out of. Diodes are made out of semiconductor materials, so most common diodes are made out of silicon. Okay? And what happens is that when you want to look at what's happening with the material, you have to look at the way that the atoms are actually arranged. Okay, so the most important thing about atoms when they're interacting with each other is the number of electrons that are in the outermost shell. Okay, so basically, when you look at an atom, you have a nucleus in the middle, and then you've got electrons orbiting around the nucleus, and the electrons can be in different shells. The ones that are in the outermost shell are the ones that interact with other atoms nearby, and so that's the most important shell to look at. So this one is, the outer shell is called the valence shell. And with silicon, you have 4 electrons in the valence shell. So when you have pure silicon atoms, each one has 4 electrons in its outer valence shell, and the electrons fit together with each other very neatly. It's almost like puzzle pieces interlocking with each other. So these electrons are interlocking, and since they fit very neatly together, it's hard to dislodge them and push them around to other spots, right? They're all sort of fit together. They're very happy where they are. They don't want to move around. Now, you guys remember that electricity is the movement of electrons, right? So if all the electrons are fitting together neatly and they don't want to go anywhere, that means that it's hard for electricity to move through a material like that. So silicon, pure silicon like this, is a good insulator. Okay? Another name for pure silicon like this is intrinsic silicon. Okay? So intrinsic silicon, or pure silicon, is an insulator. Now, scientists have figured out ways to add other chemicals to pure silicon. Okay? And in particular, they found that if they add certain chemicals, then you can end up having extra electrons in the outer valence shell. So some of these chemicals have 5 electrons in the outer valence shell. And so if you have a few of these extra chemicals sitting in your lattice of silicon, then what happens is you have a few of these extra electrons floating around. Now, these extra electrons don't fit into that neat mesh, right? They're just sort of floating around. So first of all, they have a negative charge, so we call this N-type material. And also, because they're floating around and not really situated very well, it's possible for them to move. So N-type silicon is a relatively good conductor. Okay? Pure silicon is an insulator, but when you add these extra chemicals in a process called doping, the doped silicon becomes a relatively good conductor. Similarly, you could add other types of chemicals to silicon, and these other types of chemicals have only 3 electrons in their valence shell. Okay? So we call this type of material a pentavalent material because it's got 5 electrons in the valence shell. This one is a trivalent material because it has 3 electrons in the valence shell. So what this one does is that when you add this type of material to a silicon lattice, this creates little holes or positive charges in the silicon. Okay, and it's possible for electrons to move around and jump from one hole to the next. Okay, so the holes are positive, so we call this p-type material. And since there are those holes where the electrons can jump, the p-type material is also a fairly good conductor. Okay? So I tell you about these types of materials because they're used when we construct a diode. So a diode is fundamentally two different blocks of silicon smashed up next to each other. So one side is made of N-type material and the other side is made of P-type material. Okay? And what happens is that the N-type material, like we said, it's got these extra electrons, so it's got a bunch of these negative charges over here. And the P-type material has these little holes which constitute positive charges. Okay? But right in the middle, where these two materials are smashed together, some of the negative electrons jump over because they're attracted to these holes on the P side. And so you have this region right in the middle where you don't have the extra electrons because they jumped over. And then you don't have the holes because they've been filled up by the little electrons that jumped over. So you have this region right in the middle, which is called the depletion region. Okay? And in the depletion region, the silicon acts more like intrinsic silicon because the little electrons filled up the holes and now everything is sitting together and happy. And so the depletion region does not conduct electricity very well. Okay? So if you don't apply any voltage to your diode, then you have this depletion region and the diode does not conduct. If you start applying a small voltage, I believe a negative voltage over here and a positive voltage over here, then what happens is that you're pushing more electrons in from this side. So it's shrinking this depletion region. It's getting smaller and smaller. And what happens is that it takes about 0.6 volts to completely get rid of this depletion region, to make it go away entirely. And then you have just two conducting forms of silicon and electricity can flow. So that's where the 0.6 volts comes from. And that's why it doesn't really matter how much current is flowing through there. It just takes the same amount of voltage, right? If you were to apply the voltage in the opposite direction, negative voltage over here and a positive voltage over here, then you're sort of pulling the depletion region apart. You're making it bigger. And so you're creating more of an insulator in the middle. So that's why it does not conduct in the opposite direction. Yeah?
It essentially turns it close to the way a capacitor acts, right?
So, yeah, so it is sort of similar to a capacitor because you have these two areas that have charge on them and they're separated by an insulating layer. And so diodes have some capacitance to them. And in fact, there are certain diodes that are specifically designed to work with their capacitance. They're called varactors, and they are electronically controlled capacitors, essentially. They're constructed like diodes, but we use them as electronically controlled capacitors. So we use those in modern radio equipment when you punch a button on your stereo and it tunes to a particular station that you have programmed in. What it's really doing is that it's using a varactor diode in a radio receiving circuit, and it's putting a specific voltage on that diode so that you get a specific capacitance, and then that capacitance tunes in the station that you want. So yeah.
That's all gonna be on the test, right?
Right, yeah, you'll, no.
Sorry, guys.
No, this is very, very important, and we talk more about this in ET 322, which is the next course that you guys will take. So this is not going to be on your test. This is just for general information, and I'm glad that you asked about it because it is interesting. But you don't have to worry about memorizing this stuff right now. Okay? Yeah.
How far into the terminals penetrate the material, the N and the P areas? I mean,
Yeah.
obviously, they don't go all the way through.
Right.
There has to be a gap.
Right.
Or just a little bit, almost all the way through.
You know, that's a good question, and I don't know. I'm not sure. I'll have to try and look that up and see if I can find something. I'm not sure. Okay. Other questions? Okay. So that's a little bit about how diodes are actually constructed. So you don't need to know all of that, but it is interesting, I think, a little sidebar. And that's why you have this 0.6 volt. So incidentally, this 0.6 volts pertains to silicon diodes, which is the type of diode that we use most often. But certain diodes are made out of other semiconductors, in particular germanium. And so germanium diodes have a different voltage. They're more like 0.3 or 0.4 volts here because the depletion region is slightly different when you are talking about germanium, so it takes less voltage to get rid of that. So if you have a germanium diode, you use a 0.3 or 0.4 volt drop. Okay. All right. So any other questions about diodes? Okay. So then let's talk a little bit about transformers. Okay. So transformers, the main purpose of a transformer is to convert AC electricity from one voltage to another. Okay, so that's the main purpose of transformers. You guys probably have seen, you probably remember seeing the transformers when we went to the powerhouse, right? They had a couple of different transformers. They had the really big ones outside the main power generating house. Those big old, tubs that were probably 10 feet across and maybe 10, 15 feet high. So those took the voltage that was coming out of the powerhouse and amplified it, made it higher, so that it could be transmitted down the power lines, right? So those were some transmitters or transformers. You've probably seen other transformers on a power line. You might not have known that they were transformers, but they're these little, these barrel-looking things that have two wires coming into the top, and then usually 2 or 3 wires coming out that go down to a house. Okay, so those are transformers as well. They take the high voltage that is on the power line and they convert it down to 120 volts that can be used in a house. And then, like I mentioned at the beginning of class, you guys have probably used transformers a lot, even if you didn't know it. But anytime you plug in a power source or a charger for your phone or for your laptop or for anything like that, there's a transformer inside of that which is taking the 120 volts that comes out of the wall and lowering that down to closer to 5 volts or 10 volts, 20 volts that a little electronic device needs. Okay, so transformers are all over the place. Yeah?
A lot of houses are wired for 220 as well. Is there separate transformers that are coming from the power line, or is that done at the house level?
Well, okay, so I think that a lot of houses have 240 for the for their large appliances like dishwashers, sometimes dryers, things like that. What happens is that coming out of the transformer on the power line, you have these 3 wires, and basically there's 120 volts between each pair. So there's 120 there, and then 120 between this other pair as well. So most of the wiring in the house uses just the difference between one side and the middle, but then certain large appliances use the difference from one side to the other. Yeah.
What's the 3-phase dual phase?
Well, so when you're talking about wiring up power for industrial applications, like manufacturing and things like that, they will often have 3-phase electricity. But for the house, it's typically only single phase, regardless of whether it's 120 or 240 volts. Yeah. And so that's something called a center tap transformer. So we'll talk about that in a minute. So the main purpose of a transformer, though, is to convert one AC voltage to another. So let's talk about how they actually do this. What's actually happening inside. Basically, it's really just these 2 coils of wire that are close to each other. Okay? And remember, you're passing AC electricity through these coils. So let's talk about what happens. Basically, at one moment you have a positive voltage up here and a negative voltage here. You're applying to this side of the transformer. The side where you apply the voltage is called the primary side. The other side where the voltage comes out is called the secondary side. So you're applying a positive and negative voltage on the primary like this. That pushes a current through the primary coil, right? And you guys know what happens when you put a current through a coil of wire, right? What does that coil become?
Magnetic.
Magnet. Yeah, magnetized. So, so you're creating a magnetic field over here, and electricity is kind of funny. If you put a current through a coil of wire, you create a magnet. Also, though, if you create a magnetic field and pass that through a coil of wire, you create a current. Okay? So it kind of works both ways. So when you're pushing electricity through this side and creating a magnetic field over here, that creates current on the other side, on the secondary. Okay? And the amount of voltage that you get out of the secondary is related to the number of turns that you have on the secondary. So if you have more turns on the secondary than on the primary, you get more voltage. Basically, it goes like this. The number of turns on the primary divided by the number of turns on the secondary is equal to the voltage on the primary over the voltage on the secondary. Okay? So say that you had 10 turns on the primary and 100 turns on the secondary. Then the secondary voltage is going to be 10 times greater than the primary voltage. Okay? So if you put in 5 volts, you would get out 50 volts. But there's no free lunch in electronics, okay? You can't just get out more voltage and not expect to lose something, right? So basically what happens is that if the voltage goes up, the current goes down. What stays constant is the power. So the power in equals the power out. Okay? You guys remember Watt's law, right? Power is current times voltage. So if the voltage goes up, the current goes down. It's kind of like a seesaw, right? If you get more of one, you get less of the other. So that is basically what's going on with transformers. Now, like I mentioned a minute ago, some transformers have this extra feature which is called a center tap. And so basically that's just an extra wire which is soldered on to the middle of the secondary coil. So the way that it works is that you get half the voltage from the top of the coil to the center tap, and then the other half from the center tap to the bottom. So if you're getting 240 volts altogether, then you would get 120 from the top to the center tap, and then 120 from the center tap to the bottom. Okay, so that's what's going on inside those transformers. You have a center tap, and you're splitting the voltage that way. So any questions about that? Yeah.
So why you want to scale the voltages?
So there are different applications where you need it. Some types of power supplies need this type of configuration, and we'll talk about that next time. Also, for things like wiring a house, where most of your light bulbs, computers, things like that need 120 volts, but some appliances need 240 volts. You can use a center tap and get both voltages that you need. Yeah. Other questions? Yeah.
How do they keep the magnetism control of the thing if there's magnet inside the transformer? Wouldn't it attract all the metals around the transformer?
Well, the transformers usually are not too close to lots of other metallic objects. Also, a lot of transformers have something called an iron core. So if you see two lines going down the middle of a transformer like this, that means that it's an iron core transformer. What that means is that the wires are wrapped around a form that's made out of iron. And that iron acts to channel the magnetic field. So it can help to concentrate it so that it's going from one coil to the next. So if you have an iron core like that, your transformer is more efficient. And it holds more closely to this power in equals power out ratio. There's always a little bit of inefficiency, so the power out is always going to be a little bit less than the power in, but ideally it would be like this. And when you have an iron core, it's pretty close. If you have no lines in the middle of the transformer diagram, that means that this is called an air core transformer. That means that the coils are just basically wrapped around nothing, wrapped around air. So they're just two coils of wire that are close to each other. And you still get some transfer of electricity, but it's not as efficient. Okay? So the iron core can help to channel the magnetic field. Yeah. Other questions? Okay. So we call the number of turns on the primary over the number of turns on the secondary, we call that the turns ratio. Okay? And in fact, it's usually written as the number of turns on the secondary over the number of turns on the primary. If there are more turns on the secondary, then you get more voltage coming out. And we call that a step-up transformer, because the voltage gets stepped up. If there are fewer turns on the secondary than on the primary, you get less voltage out, so we call that a step-down transformer. Okay? Yeah?
Can you throw, just real quick, a real life example? So we're getting 10,000 volts in, and,
Sure.
and we want,
Yeah.
or
So we've got,
say 12,000, and we want 120 amp.
sure, 10 or 12 kilovolts here. And we want to get, well, say 240 out of the whole transformer, right? So let's figure out what turns ratio we would need in order to make that happen. So we know that the turns ratio is going to be, well, voltage on the secondary over voltage on the primary. Hmm?
Be 500 to 1, right?
Yeah, I think so. So for every turn on the secondary, you would have 500 turns on the primary. So you could, if you have 100 turns on the secondary and 50,000 on the primary or something like that, as long as you maintain this ratio, you would be all set. Yeah.
But in reality, it's actually done in steps. This is just one jump, because this will create a lot of heat at that one concentrated point. So when your main 10,000 or 12,000 volt line comes down to your local neighborhood, you have that substation. And that's what breaks it down to like 240. And then the other one, powerful, then breaks it down to the 120.
Right. So there are different steps, right? So when you have the really big power lines that are like running along I-5, they might be hundreds of thousands of volts. And then you have a substation that breaks it down probably to 10,000. I think the lines that run above the houses are still in the thousands of volts. And then the transformers that sit on the pole take it from several thousand down to the 240 or whatever that's going to the house. But yeah, there are several steps that go from very, very high voltages down to the lower voltages. Mm-hmm. So yeah, other questions? Yeah. Okay. So that's the idea about how transformers work. Okay. Oh yeah, so when we are testing transformers, we want to make sure that they're working right. And there are a couple of failure modes that we want to look for. So first of all, if you have a lot of heat in a transformer and it's not cooled properly, what can happen is that some of the insulation on the wire can melt. And if that happens, then you can get electricity going where it's not supposed to go. It could jump from, one side to the other or something like that. And when electricity goes where it's not supposed to, that's called a short circuit. So you can look for short circuits in a transformer. Short circuits are bad. The other thing that could happen if it got really hot or if it was handled poorly is that the wires could break somewhere. And if they break, then the electricity can't go through them. Another word for a broken wire is an open circuit, okay? Because there's an opening between one side of the wire and the other. So an open circuit is also bad in a transformer. So when you are testing transformers, you want to look for shorts and opens, okay? So both of those things are things that you want to avoid. Finally, there's one more thing that I wanted to talk about before we go on to the lab preview. And what I wanted to talk about was AC voltage and how we measure it, how we quantify it. Okay? So in the past, we've talked about peak-to-peak voltage when we are talking about AC signals, right? So peak-to-peak voltage is the amount of voltage from the highest peak to the lowest peak of your signal. If you had a sine wave like this, then your peak-to-peak voltage would be the voltage from the very top of your wave to the bottom. So that's sometimes abbreviated VPK dash PK, right? Peak-to-peak voltage. So that's one way of quantifying AC voltages, but that's not the only way, okay? Another way would be looking at the amount of voltage from the top of your wave down to the middle line, or 0 volts. So that could be called the peak voltage, okay, or VPK for short. Yet another way of quantifying AC voltages is something called RMS. So RMS voltage, in order to get the RMS voltage, you use a formula and for sine waves, we say that VRMS is 0.707 times V peak. Okay? Yeah, 0.707 times V peak. If you measure an AC wave with a multimeter, that multimeter is going to give you the voltage in RMS. Okay? So if it says 120 volts coming out of the wall, that's 120 volts RMS. So that means that the peak-to-peak, or the peak voltage is actually even higher, and the peak-to-peak is even bigger than that. Okay? So if you're measuring it with a meter, it's giving you the voltage in RMS. That's true with the meters that we have in the lab. That's true with the meters in multisim. It's true with almost any digital multimeter that you use, unless it specifically says a different voltage. The voltage that it's showing you for AC signals is in RMS. Okay? All right, so with that said, let's talk a little bit about today's lab. Any questions before I go on? All right, then let's talk about the lab for a few minutes. So the first part of the lab is going to be in multisim. You're going to get that from the ET302 folder and this folder that says L19 Diodes and Transformers. We're going to start with this first circuit, PS1A. And with this circuit, you're going to be you're going to fill out a table in your lab book that shows the diode voltage, the resistor voltage, and then the amount of current that's flowing. Okay? You're going to do that, and then you're going to vary the voltage source over here when you do it. So we're just going to run this the first time. How much voltage do we expect to see on the diode? Well, first of all, is the diode forward biased or reverse biased?
Forward.
Forward, perfect. So is the current going to flow?
Yes.
Yes, exactly. And how much voltage do we expect to see?
Do we know what kind of diode it is?
Ah, good question. Yes, it's a silicon diode. So yeah, somewhere around 0.6. You know,
Is that the
between-
voltage we're measuring, or are we measuring the voltage through it?
Well, voltage is always measured between 2 points. So we're measuring the voltage difference between one side and the other. Yeah?
The diode is reverse biased because you're increasing depletion. Does that imply that the resistance goes up the larger the voltage difference with reverse bias condition or not?
Well, so when it's reverse biased, essentially no current flows through it, right? So it has essentially infinite resistance. Yeah, it's like an open circuit. So
you treat it just like an open wire or something.
yes, that's right.
If you have enough voltage on it, or in reverse bias, will it go through?
Yeah, eventually, if you put too much voltage on it, the diode will break and the current can start flowing. And that goes back to your question earlier about the rating of the diode. So each diode is rated for a certain amount of reverse voltage. And as long as you stay below that, you should be okay. If you go above it, then the diode can break down. And I don't know what that rating is for these particular diodes, but
50.
Okay, 50 volts. There you go. So as long as you're below 50 volts, you should be okay. So
Would that be 4.4?
So the voltage across the resistor should be about 4.4 because we should have about 0.6 across the diode and a total of 5, right? So that's what we would expect to see, somewhere in that range. Remember, it's somewhere between 0.5 and 0.7 on the diode. It's not exact, but it's somewhere like that. So we're seeing about 0.55 volts across the diode. So the remainder is made up across the resistor. And the amount of voltage that we have across the resistor tells us how much current we're getting, right? We have 4.45 volts across the 1,000 ohm resistor. So that tells us that we have 4.45 milliamps flowing through the whole circuit. Okay. So the book asks you to change the voltage on your battery here. And you're going to do that a couple times. What you should see is that when you do that, the voltage on the diode changes a little bit, but not very much. Whereas the voltage on the resistor changes quite a lot, right? Last time it was 4 volts, now it's 9 volts. The voltage on the diode is still, between 0.5 and 0.6 volts. Yeah?
So we're getting the current reading from that final DMM there.
Mm-hmm.
But that's not taking into account any resistance from the diodes, correct?
Well, what we know...
When you have a higher total resistance of about 1,000 ohm resistor plus the diode?
So we're measuring the voltage across the resistor, right? We're measuring 9.4 volts across that resistor. And if we know that we have 9.4 volts across the resistor and we know how much resistance we have, we can use those numbers to, in Ohm's law, to calculate the amount of current that we have. So
That's just for that one part of the circuit.
I guess what he's asking is, what does the diode provide any resistance?
well, it's not resistance in the same way that resistors provide resistance, right? So with resistors,
Basically, it's not calculated in total resistance.
well, yeah, you don't just add, there's not a number that you can just add up like you would add up resistors in series. So it basically, you deal with diodes differently when you are calculating the voltage and current in a circuit. So with a diode, you treat it like a voltage drop rather than a resistance. So really this is, if we were analyzing the circuit, what we would say is we've got a 10 volt source here and then a 0.6 volt drop.
Gotcha.
And then, so we would say that we have about a 9.4 volt source to the left of our resistor, and then 0 volts on the right-hand side, so we could analyze it that way.
So because you're taking out that voltage drop, the resistance is kind of eliminated, or not eliminated, but it's
Well,
not.
that's how we account
Yeah.
for it.
Okay.
Yeah. Yeah, other questions? Yeah.
So very much by current, you can use 9.4.
Yeah, so exactly. So we know that we have 9.4 volts across 1,000 ohm resistor, and since we know that, we can use Ohm's law and figure out the current. Yeah. Other questions? Okay, cool. So you're going to go through and change the voltage around a couple times to record the values in your table. This is a similar situation, but now you have two diodes. So are they forward biased or reverse biased?
Forward.
Forward, exactly. So now when you look at this circuit, you're going to take out two diode voltage drops when you're analyzing the circuit. So you would start off with 12 volts and then subtract, about 0.6 volts twice. So yeah, about 1.2 volts. So you should be left with about 10.8 volts across this resistor. And then you could use that to calculate your current. So we're going to do the run the simulation here, and we should see something about like that. So the diode drops are not exact, so we ended up with about 11 volts across the resistor, but then we know that it's a 6 kilo ohm resistor, so we can do the calculation and come up with the amount of current that's flowing through it. Okay. So you're going to do that. Again, you're going to vary the voltage on the voltage power source here. And again, you should see that the voltage across the resistor changes quite a bit, where the voltage through across the diodes does not change very much. Part 1C. Is this diode forward biased or reverse? Exactly, reverse. So is the current going to flow?
No.
No. Right. So in that case, how much of the voltage should be across this diode?
None.
I'm still going to take that 0.6.
No, not exactly. So, yeah, all of it. Exactly. All of the voltage is going to be across the diode. Another way to think about that is that there's no current flowing through the resistor, right? So voltage is current times resistance. If you have zero current, you have zero voltage across this resistor. So both sides of the resistor are at the same voltage. The right-hand side is connected to ground, so the right-hand side is at 0 volts. Therefore, the left-hand side must also be at 0 volts. So the right-hand side of the diode then is at 0 volts. And we know the left-hand side of it is at 12 volts, right? It's connected straight to the 12 volt supply. So all of the voltage of the circuit is across this reverse bias diode. Okay. So if we run it, we should see that. So there you go. So that's that circuit. Now you have a circuit where you have two branches that are in parallel. Okay, so you're going to run that. You're going to change the voltage a few times and see how that works. Now we're on to another circuit that's using a transformer. Okay? So first of all, the voltage supply looks a little bit different. Earlier we had voltage supplies that looked sort of like this. This indicates a DC voltage supply. Okay? Over here we've got a voltage supply that looks like this. AC, exactly. It's got this little sine wave, which is the wave form that we use with AC electricity. So this is an AC source. And you'll notice that the voltage is specified two different ways. It says 141.42 up here, and then it says 100 volts RMS. So what this is showing you is it's showing you the peak voltage, which is 141, and then it's showing you the RMS voltage, which is 100. Okay. So if you were to open this voltage source up, you can see that you can specify the RMS voltage or the peak voltage up here. But they're linked together, right? So if I change one, the other one changes automatically. Okay, so because they're related by that formula, you can't change them independently. So if you change one of them, it updates the other one for you automatically.
So that's 141 times 0.707.
Yeah, it comes out to be 100. If I put in 100 volts on the top, it would be clearer. 100 times 0.707 comes out to be 70.7. So, but when the book asks you to enter a voltage, it's talking about entering an RMS voltage. Okay? So you'll put that in. This has a turns ratio of 0.25. That's the primary, the secondary turns ratio. So that means that for every one turn on the primary coil, there are 4 turns on the secondary coil. So is that going to be a step up or a step down transformer?
Step up.
Step up, exactly. So if we put in 100 volts, how much voltage do we expect to get out?
400.
Yeah, about 400. So let's see. If we run this. Open this up. Yeah, we get about 400 volts out. Now, you'll notice that we're reading a meter. So what type of voltage are we reading?
RMS.
RMS, exactly. So we're seeing 400 volts RMS when we put in 100 volts RMS. Right? Okay, so you're going to fill out a table in your book. You're going to change the some of the resistance values around, or I'm sorry, you're going to change the turn ratio around. So to change the turns ratio, you just double click on here and enter whatever turns ratio you want. Then finally, you're going to, in the last circuit, you're going to be measuring the current in and the current out. Okay? So we said that if the voltage goes up on the output, the current goes down. Right? So you guys will be measuring that as well. And that's what you're going to do in multi-site. Any questions about that? All right. Then after that, you're going to be working on a real transformer. Okay, so you guys are all going to get a transformer that looks like this. They come in a little box like this. You'll pick them up from box of transformers at the back of the room. And what we want to do is we want to measure the resistance of the primary coil and also the secondary coil. Now, these are coils of wire. Do you think they're going to have a big resistance or a small resistance? Well, it's just basically a long wire that's wrapped up. So wire doesn't have very much resistance. So these coils are actually going to be pretty low resistance, probably under 10 ohms. So what happens is that when we're measuring low resistances, we have to be careful that we're just measuring the wires and we're not measuring the leads that are connected to the DMM themselves, right? Because the leads are just wires and we're measuring more wires, so you kind of have to figure out what's what. So what we do is that the first thing that we do before we measure anything else is we measure the resistance of the leads themselves. The way that we do that is that we just connect one lead to the other one, and we put the meter into the lowest setting, and we record whatever voltage or whatever resistance we see. So that'll probably be less than 1 ohm, but you figure out what that is and you write that down. So that's the first measurement you're going to make, and you're going to write that in your book. Then what you do is you attach the leads to the two ends of the coil, okay? And then you measure the resistance again, and you write down that value. You write that down in your book. So that's going to be basically the resistance of the leads as well as the resistance of the coil. And then the third thing you do is you subtract the resistance of the leads from the total resistance. And that difference is going to give you the resistance of just the coil. Okay? Yeah?
Do they make a DMM with dedicated leads that like zeroes itself so that automatically pulls that out?
What they do is they make something called a four-wire multimeter for measuring things that have very low resistance. And the way that that works is that so basically So like I said, most meters don't measure resistance directly, right? What they do is they create a small amount of current that flows through something, and then they measure the amount of voltage that is created, okay? So, so if you have a typical meter, you've got a little current source in here, and you know how much current you're creating, so you're making 1 milliamp, and that flows out through one lead, and then it flows through a resistor, and then it flows back in through another lead, and you measure the voltage there, and then you use Ohm's law to figure out the resistance, right? So in that case, you're sending the current through this entire lead, through both leads, and so you're really measuring the resistance of both leads. what happens with 4-wire meters is that there are 2 sets of leads. So you still have this little current supply here, and that is still hooked up to your resistor. But when you're measuring the voltage, you have a separate set of leads. So you've got another set of leads over here. And this is where you measure the voltage between these 2 leads. So there's not really any current that flows through these leads over here. Okay? All of the current is flowing through these leads, so you don't have any current flowing through these outer leads, and so you're not measuring the resistance of these outer leads, you're only measuring the resistance of this thing that you actually want to measure. So that's what people do in the real world when they're trying to measure very small resistances. Okay? And that does take account for the leads. Yeah. Or it tries to eliminate the resistance of the leads. Yeah. Other questions? Okay, so you're going to measure the resistance of the black leads, and then you're going to measure the resistance of the green leads. Now, these green leads, you'll notice that there's 3 of them, right? So this is a center tap transformer. The 2 solid green wires are the outer parts of the transformer, and then the green wire with the yellow stripe on it is the center tap. Okay? So you will measure all of those resistances, and then you're going to draw a picture that indicates how much resistance is in each part of the transformer. So it can just be a simple diagram like this, and say the first one has, the primary coil has 10 ohms, the secondary coil has 20 ohms. You would just draw something like that, okay? It doesn't have to be fancy, just something like that. And then for the next part of the lab, you're actually going to put an AC signal into the transformer, and you're going to measure the input and the output on the oscilloscope. Okay, so you're going to use the function generator to create an AC sine wave. You're going to put that into the transformer, and then you're going to use the oscilloscope to measure both the input and the output signals. So you're going to be showing two traces on the display of the oscilloscope at the same time. Okay? So you're going to need 2 different probes. You're going to have to check out 2 probes from the back window when you go and get those. Okay? So you'll hook one side up to the input and the other side out to the secondary, the output. And then you will measure the input and the output voltage on the oscilloscope. And then there's a couple of review questions at the end of the lab that you guys are going to answer as well. So any questions about that? Okay. Then I will take lab and I'll let you go. I'm sorry, take attendance and I'll let you go to lab.